Hello and welcome to Controllers Tech. In today's video, we're starting a brand new series focused on enabling Ethernet connectivity on low-end STM32 microcontrollers. I've already created a complete series earlier that covered how to use the Ethernet peripheral in STM32 with the LWIP stack. That series mainly focused on the PHY-LAN 8742, which is commonly found on some STM32 Nucleo and Discovery boards. However, not all development boards include a built-in PHY chip. Even if your board doesn't have one, you can still solder an external PHY and use the Ethernet peripheral, as long as your MCU supports it. But this is where the limitation comes in. Many lower-end or lower-pin count STM32 microcontrollers simply don't include the Ethernet peripheral. For such MCUs, we can make use of external Ethernet modules that communicate through SPI or I2C interfaces. This is exactly why I decided to create a new series, to bring Ethernet capability to entry-level MCUs like the STM32F103, and even some of the STM32F4 series. Throughout this series, we'll be exploring the major communication protocols, TCP, UDP, HTTP, and even MQTT, so you'll be able to build a wide range of connected applications. This video is the first part of the series. Today, we'll start by learning how to connect the Ethernet module to an STM32 board, configure the necessary peripherals, and finally perform a ping test, both with a static IP and using DHCP. For this series, I'll be using the W5500 Ethernet module by Wiznet. It communicates through SPI, which means it can be used with almost all STM32 boards, regardless of whether they have a built-in Ethernet peripheral or not. Before choosing the W5500, I also considered the ENC28J60 module. The ENC28J60 is quite popular because it's affordable and widely available, but it comes with a few important drawbacks when used with STM32 microcontrollers. The biggest limitation is that it relies heavily on the MCU to handle the entire TCP IP stack, which means you have to use a software stack like LWIP on your STM32. This approach increases CPU load, consumes more flash and RAM, and can cause performance drops when handling multiple connections or transferring large amounts of data. The W5500, on the other hand, is much more efficient. It includes a built-in hardware TCP IP stack, so most of the protocol processing happens directly inside the chip. This not only makes it faster and more stable, but also significantly reduces the load on the MCU. Additionally, it supports up to 8 simultaneous socket connections, has a 10 or 100 megabits per second interface, and comes with a 32 kilobytes internal buffer, ensuring smoother and more reliable data transmission. Now that we understand why the W5500 is the better choice, let's begin with the setup. Before we start creating our STM32 project, we first need to download the required library files. Search for the Wiznet IO library, and open their official GitHub page. Download the entire repository in zip format and extract it on your computer. We'll include the necessary files and folders into our project as we move forward, depending on what's needed for each step. Let's begin by opening STM32CubeIDE, and creating a new project. For this tutorial, I'll be using the STM32F103 microcontroller. Give your project a suitable name and click Finish to proceed. The first step is to configure the clock settings. Enable the external high-speed crystal to provide the system clock source. The board is equipped with an 8 MHz crystal oscillator, and we'll configure the system to run at its maximum frequency of 72 MHz. Next, go to System Core, Sys, Debug, and enable Serial Wire Debug. This will allow us to program and debug the microcontroller through the SD-Link interface. Now, let's configure the SPI peripheral. We'll be using SPI1, so enable it in full duplex master mode, as we need two-way communication with the W5500 module. Make sure the data size is set to 8 bits, and the first bit is transmitted as MSB first. To ensure proper operation, configure the prescaler so that the SBI clock remains below 25 MHz. Here, I've set it to approximately 18 MHz, which works reliably with the W5500. Keep the clock polarity low and clock phase on the first edge, which corresponds to SBI mode 0. Also, set the NSS, chip select, signal type to software, since we'll be handling the chip select pin manually in our code. Once that's done, you'll notice that the three SBI pins, SCK, MISO, and MOSI, are already configured. We'll now add two additional pins, one for chip select and another for reset. Set both of these pins as GPIO output, and name them CS and reset respectively. Next, let's configure a UART interface to view logs on the serial console. I'll be using UART1 for this purpose. Pin PA9 serves as the TX pin, which should be connected to the RX pin of the USB to TTL module, such as the FD232. Now, go to System Core, GPIO, and set the GPIO output level for both CS and reset pins to high. This ensures that the pins are initialized in a high state by default when the MCU starts. Also, set the output speed for both pins to high to ensure reliable switching. That completes all the necessary configurations. Click Save to generate the project files. Before moving forward, let's take a quick look at the connection diagram. Here you can see the wiring between the W5500 module, STM32F103, and the FD232 USB to TTL converter. The W5500 module is powered directly from the MCU's 3.3 volts supply. The SPI pins, PA5, PA6, and PA7, are connected to the SCK, MISO, and MOSI pins of the W5500 respectively. Pin PA4 is connected to the CS pin on the module, while PA3 is connected to the reset pin. The Ethernet module connects to the router via an RJ45 cable. Using this setup, we can obtain an IP address automatically via DHCP, but I'll also show you how to configure a static IP address for cases where a router isn't available. Finally, the UART1 TX pin, PA9, connects to the RX pin of the FD232 module, which will allow us to view debug logs on a serial console. That's all for the hardware setup. Next, we'll start including the necessary library files into our project. Open the extracted folder that contains all the Wiznet source files. We'll now add these source and header files into our STM32 project. To keep things organized, create a new folder inside the drivers directory of your project. This will help separate the Wiznet files from the automatically generated ones. Once the folder is ready, copy these 4 files into the newly created Ethernet folder. Next, we need to include the files specific to the Ethernet module's chip type. Since I'm using the W5500, copy the entire W5500 folder from the extracted files and place it inside the Ethernet folder in your project. Now, navigate to the Internet folder inside the Wiznet library. If you plan to use DHCP and DNS features, copy those folders as well and place them in the same Ethernet directory. That's all we need to include for now. We'll bring in other files later if necessary. Next, open the WIZCHIP configuration header file. In this file, you'll find a section where you need to define the specific chip you're using. There's already an example provided for reference. So, let's define W5500 here. Once you do that, the conditional part of the code meant for other chips will automatically be excluded. We don't need to make any additional changes in these configuration files at this point. Now, right-click on your project and open Properties. Go to C++ Build, Settings, GCC Compiler, Include Paths. Here, you need to add the path to the Ethernet folder you just created inside the drivers directory. Use the Workspace button to easily navigate, and select the correct path to the Ethernet folder. I've also prepared a set of files to port the Wiznet library to STM32, so let's include them as well. Copy the two files, WIZCHIP port.c and WIZCHIP port.h, into the same Ethernet folder. Now, let's take a moment to understand the purpose of the port file. At the top of this file, you'll find definitions for the SPI and UART handlers that your project uses. You'll also see an option to enable or disable DHCP. If you prefer to work with a static IP, simply set the DHCP option to 0. Next, you can edit the network configuration parameters for your device, such as MAC address, IP address, subnet mask, and gateway. The default MAC address provided here is a random value, so feel free to change it if needed. If DHCP is disabled, the IP address defined here will be assigned to the module. However, if DHCP is enabled, this information will be automatically overwritten when the module obtains a dynamic IP from the router, except for the MAC address, which always remains unchanged. In the next section of the port file, you'll find functions that control the chip select and reset pins of the module. If you've already assigned and named these pins correctly in CubeMX, there's no need to modify anything in these functions. In this port file, we primarily call a single function, W5500 init. This function is responsible for initializing the Ethernet module and displaying key status information on the serial console. Let's go through what happens inside this function step by step. First, the function performs a hardware reset sequence for the W5500 module, ensuring it starts from a clean state. Once the reset is complete, it registers the callback functions for both chip select control and SPI communication. These callbacks include the functions that handle reading and writing data between the STM32 and the W5500 through the SPI interface. Next, the function initializes the W5500 chip and reads its hardware revision number. If the initialization is successful, the chip returns a version value of 0x04, confirming that communication is working properly. After this, the function checks the Ethernet link status to verify if the module is physically connected to the network. It attempts this check up to 10 times, with a 500 millisecond delay between each retry. Once the link is detected, the function proceeds to configure the network settings. If DHCP is enabled in the configuration, the function will initially set only the MAC address and then start the DHCP process. It calls the DHCP run function repeatedly, to request an IP address from the router. This process allows up to 20 retries, again with a 500 millisecond interval between each attempt. If the IP address is successfully obtained, the function retrieves the IP, gateway, and subnet mask assigned by the DHCP server, and stores this information in the W5500 chip. However, if DHCP fails to acquire an IP address even after 20 attempts, the module automatically switches to static IP mode and applies the predefined static network configuration from the code. In case DHCP is disabled from the start, the function simply loads the static IP configuration directly into the W5500 chip. Once the network configuration is complete, the function moves on to set up the DNS parameters. Finally, it prints all the relevant network details, such as IP address, subnet mask, gateway, and DNS, on the serial console, allowing you to verify that everything has been configured correctly. Alright, now that we understand how the initialization works, let's move on and see how to use this library in our STM32 project. Inside the main.c file, start by including the header file WIZCHIP port.h. This will allow us to access all the functions and definitions needed to interface with the W5500 module. Now, inside the main function, after all system and peripheral initializations are complete, call the function W5500init to initialize the Ethernet module. This function handles the complete setup process we discussed earlier, including resetting the chip, checking the link status, and configuring the network. If the initialization is successful, the function will return 0, indicating that everything is working correctly. That's all we need to do in the code for now, so let's go ahead and build the project. You might notice several errors appearing during the first build. In my case, this happened because I accidentally copied duplicate files inside the source directory. After deleting those duplicates, all the errors disappeared. When you build again, you may still see a few compiler warnings. These can be safely ignored, as they won't affect the functionality of the program. Next, open your serial monitor to view the log output. Make sure the baud rate in the serial monitor matches the one you configured in CubeMX for the UART interface. Now, flash the project to your STM32 board and wait for the process to complete. Once the board starts running, you'll begin to see logs appear in the serial console. Let's go through what's happening here. The main log output begins after the module initialization. First, the program initializes the W5500 chip and then checks the link status. Although the Ethernet cable is already connected, it usually takes a few seconds for the module to detect and confirm the network link. After the link is detected, the module proceeds to configure the network via DHCP. Once DHCP successfully assigns an IP address, it automatically sets up the DNS configuration. Finally, the console displays all the important network information, including the IP address, subnet mask, gateway, and DNS server details. Now that we have a valid IP address, let's test it by performing a ping. Since the module is directly connected to the router, we can ping it from any device on the same network. My computer is connected to the router via Wi-Fi, and as you can see, the ping is responding perfectly, confirming that communication is working as expected. If I try to ping any other random IP address, of course, there's no response, which is normal. So with just minimal configuration, we've successfully established communication with the W5500 Ethernet module, and it's responding to network requests properly. If you don't have access to a router, you can still test your project locally by using a static IP configuration instead of DHCP. To do this, simply set use DHCP to 0 in your code. When this option is disabled, the module will automatically use the static IP settings defined in the configuration, and this network information will be stored directly inside the W5500 chip. Along with configuring the module, you also need to set up the Ethernet network settings on your computer. In this example, I'll demonstrate the configuration process on a Mac, but the same steps apply to Windows and Linux systems as well. You can also find a detailed explanation and screenshots in the article linked in the video description. First, connect the RJ45 Ethernet cable directly between your computer and the W5500 module. Once connected, the Ethernet interface should automatically appear on your computer. Now, let's configure it according to the module's network setup. Make sure that IPv4 is set to be configured manually, not automatically. Since the gateway address of the W5500 module is 192.168.1.1, your computer's IP address must be within the same subnet, but it should be different from both the gateway and any other device on the network. You can safely assign any IP between 1.2 and 1.254, given that no other device is using the same IP. Also ensure that the subnet mask, gateway, and DNS values match those defined for the W5500 module. That's all that's required, setting use DHCP to 0 effectively switches the module to use a static IP. Now, let's rebuild and flash the project again. Once the program runs, open the serial console. You'll see that the logs confirm the module is now using a static IP address. Let's try to ping this IP address to verify the connection. Initially, you might notice that the ping fails. As you can see in my case, I'm unable to ping the static IP at first. This issue doesn't occur for everyone, but on Mac OS, it often happens due to the network connectivity order. At the moment, my computer is also connected to Wi-Fi, which takes priority over the wired Ethernet connection. So, let me disable Wi-Fi, and try pinging again. Now you can see the ping is working perfectly, and the response time is actually faster compared to when using DHCP, which is quite common, since static IP communication avoids the overhead of address negotiation. However, if I reconnect Wi-Fi, the computer will again fail to reach the static IP, because of the same priority issue. I haven't faced this behavior on Windows, so it might be specific to Mac OS. In any case, we've now successfully demonstrated both DHCP and static IP configurations, and both are working exactly as expected. Before wrapping up this video, let's quickly take a look at the TCP server example provided in the Wiznet library. Open the library folder, navigate to the application directory, and copy the loopback folder into your project. This loopback example contains ready-to-use functions that can create TCP and UDP echo servers as well as clients. In this video, we'll focus on testing the TCP echo server and see just how simple it is to implement. Before running the example, if you'd like to view the loopback function logs on the console, you'll need to enable debug output. To do that, simply define the macro loopback debug in your project. Once defined, you'll be able to see detailed loopback logs during runtime. Next, include the loopback.h file in your main.c file. Then, create a buffer to temporarily store incoming TCP data, which will later be sent back to the client. Inside the infinite loop, call the function loopback_tcps to start the TCP echo server. The first argument to this function is the socket number, which we'll discuss in detail in the next video. For now, just pass 0 as the socket number. You can choose any available TCP port for the server. Here, I'm using port 5000. Now, let's build and flash the project to the board again. At this moment, my RJ45 cable is still connected directly to the computer, so DHCP is unable to obtain an IP address automatically. That's why you can see the failed to obtain IP message in the console. Let's fix that by connecting the module to the router and resetting the board. Perfect, the module has now successfully obtained an IP address, and the TCP server is listening for incoming connections. Let's try connecting to this server from the computer. As soon as a client connects, you'll see a message on the serial console showing the IP address of the connected client. Since this is an echo server, it simply sends back whatever data it receives from the client. Let's test that by sending some text. As you can see, the server immediately echoes the data back, exactly as expected. So the TCP echo server is working perfectly. When we disconnect from the server, the socket automatically closes. Because the loopback function is continuously called inside the while loop, it goes right back into the listening state, ready to accept a new connection. Everything is working smoothly so far. We've successfully connected the W5500 Ethernet module with STM32 via SPI, configured the module, used DHCP to obtain an IP address, pinged the module successfully, and now even implemented a TCP echo server on the STM32. In the next video of this series, we'll move one step further, configuring an actual TCP server that can store received data or process it for specific applications. That's all for this video. You can download the complete project from the link provided in the description below. If you have any questions, feel free to leave a comment. Thanks for watching, and have a great day ahead.